All right, me. All right, so now, topic of the lesson is to learn how to use OBS. No, is to construct the simulator I have shown you before, and I'd like all of us do this. Like I like you to do the work. Okay. So let's start. We're starting a new project, and to start a new project, a good practice is to create a directory where to put the new project. mkdir simple simulator in class. If you want to call the directory spaceship, you're free to do so. Right now I am into the directory. So far so good. Then what do? We open our favorite editor. Now you can open your systems. I will not. I will use Emacs. But before that, we need to create a CMake file just for our project to bring in the stuff we need. And if you remember, the CMake file are never created, are always copied. So I will go in another folder of the system and harvest for a CMake list. And then I will massage it until I'm happy. Okay? There was the one of build system, P01 compilers and build systems. No, there was the exercise, I think. Exercises, 01 compilers and build systems, Minicore, and there was a CMake lists. Just copy a CMake list from someone else to me. What I'm doing is like copying, and then I go back into the directory until I find something that I want. Okay? And then, of course, this will not be what I want, and I have to edit it. The project, via. Then we proceed with the polishing. Project which will become simple simulator. Then this I don't like. Like you can try to use this find path, or you can butcher the things like me. Delete. Include directories. Eigen is a library that, if you have a proper installation, is installed in user include eigen3. So just say include this directory instead of finding the package, because it disturbs me to search for eigen. And then there is another horrible package that I have to include for this project, which is OpenCV. Open Computer Vision Library. I need it only for loading the images and to show the things. Okay? OpenCV, I think. Hopefully it's called this way. And if not, Google for where is OpenCV. Of course, I have it in the other folder, so I will discover how this package is called. OpenCV. Oh. OpenCV. Quit. Die. OpenCV. Just copy the thing. Okay. This is the name. And then I also write required. Because in a way that everything gets broken if my system doesn't work. And then basta. I'm happy with that. Let's see what happens, right? I issue, now I have this splendid CMake list into the folder which was simulator in class. That's the tilde, which is the thing that the saved file, ignore it. I'll create a build directory, ICD in build, and then I issue the CMake. I tell CMake, try to run the CMake of the upper floor. Oh, it found something. I'm blessed because it found OpenCV. Okay. Now it has found OpenCV, but then how do I know? You remember, once I include a package, I have to figure out what is the variable where CMake writes the include flags, and what is the variable where CMake writes the library flags. Remember, looking for a package results in figuring out where the include files are and where the libraries are. Okay, so now it's not a case that I run CMake in this open fashion, because it has done something. It has written tons of stuff into this folder, and what I'm interested in is in the CMake cache, which is the place where CMake, the file where CMake writes all the variables that it detects. I open it naively, and then not knowing anything, I just look for CV. Oh, yes, OpenCV yes. Only OpenCV it has found. Include. Oh, well, it has only found the OpenCV. I don't know what to do with it, but then let's be happy with that. I mean, BG. Okay. But it has found something. I'm comfortable. Then we don't want to write everything on the same level. So what we are going to do, open another terminal, we go into our original folder and we create a source directory, just for cosmesis. So that we have a top level CMake that then recurs into the source directory. We like? Yes, we do. And so into the CMake, I have to say, hey, CMake, please go into the source directory, because there will be work to do inside. Make sense? And then we enter in the source directory and we populate it with the initial CMake list. Well, now I entered into the source directory, I wrote an inner level CMake list, right? And I don't know what to do now, and so I start programming. What am I gonna need? I'm gonna need a small package, because in order to implement the simulator, there will be three things that I need: transforms, which means orientations and positions on the plane, and I need vectors, 2D vectors. That's all I need. That clear? Yes? No? Maybe? Very good. And so now I'm in the directory source. I add. So aspetta. I add library. I'll create a library. Simple simulator, where I will that for now it will contain only one thing. Will contain only a small package named linear algebra 2D. Okay, guys? Do we buy it? And also, in order to test this program, of course, this file I didn't yet create. I just conjuncture in my head. Add executable, I think. Otherwise, I have to look back. And I'll create an executable that links against the same library, and then I will have to say target link. I will have to say that this executable requires to be linked against the simple sim library that I just generated. Just to be more verbose. Okay. Of course, I don't have neither linear algebra 2D nor simple C, but let's proceed, right? Okay. So now I am entering in the folder, like to see the layout of the directory. Now I have a source directory. I enter into the source directory, and then there is the CMake list that I have just written, and so I expect now here to write the files. How did I call the files? Linear algebra 2D. Horrible. Not even linear algebra 2D. It's simple geometry 2D. And given that I am obnoxious with the names, I will change it. Because the name should state what the program does. Otherwise, you get 2D. Sorry, but I'm fixed with these things. Otherwise, okay, rebaptize. And then let's edit the files. Probably you don't see. No. How tall should I put the editor so that you don't see exclusively my skull? Is this fine? Yes. A bit longer because programming on a C64 is tough. Already huge font. Okay, now opening a splendid file which we will call geometry2D CPP. Well, let's start from the geometry2D.h. geometry2D.h. It's a good H file. Let's start with pragma once. If it's an header file, we want to include it once. And then we need to create some classes. Okay, let me create a vector. Call it vector2, which will be a vector of 2 dimensions. No heap allocation. Everything will be contained in the class itself. Give me a name for this struct. Vec2. Vec2. It's a good one, right? All right. Then what do I need? Let's say we are gonna work with floats or double. Which precision do you want? Let us be, looking at the future. Let's say that we are gonna select later the precision. For now, we choose the precision, so the type, to be scalar. Like for us, double or float for us is a scalar, right? So we would like to create an alias in the remaining of the program that is the scalar type that we're gonna use. Okay? And now I'm introducing a new thing that will become familiar later. So in the reminder, I will be using scalar. Each time I write scalar, in fact, I'm meaning float. But by writing this thing, using the name equals data type, is the type def of C. But it can be used in a more articulated manner. This will be useful when we will gap into templates for those that will do it. Okay? But in this way, and then nah. And then let me also, my heart is singing to climb, but let's go. Let me also do one thing, that in Vec2, maybe later on I might want to extend it to support arbitrary dimensions, right? But I want the class not to use any sort of heap allocation. Because heap allocation, when not needed, it's bad. Okay, especially for these small objects. I call it static int dim, right? I have a variable which is called dim, but it's not a variable that it's static. What does it mean if you write static inside a class? You see, it has a special meaning because it's a variable which is not allocated per object, there is one instance of variable which is common to all classes. Okay? Clear? And there is a caveat on how to declare const variables, but I will now use another keyword of C++, which is constExp. ConstExp tells the compiler, hey compiler, this is not a variable. This is a constant at compile time. Okay? And by knowing that it is a constant, the more the compiler knows, the better things it can do. Because if it knows that this is a constant that is big 3, and if I have a for loop that spans over 3, it will look an SSE instruction that in one go will do the 3 instructions that I need. Okay, the more information you give, the better it is. I can also put it this way, static constant dim equals 2, right? But of course, you have to initialize it on the spot if you write constExp. Otherwise, the compiler doesn't know. And then where are we going to store the values? Two variables, an array. An array? No, it's a vector. Vector of 2 dimensions. Vector of n dimensions in general. Or, let me write it dim capital for self-consistency. Come on. What else do I need in a vector of 2 dimensions? In a vector of arbitrary dimension, but that is specialized for 2. Come on. Eh? No. I have the class. I have the class. What? Yeah, in the heap. You want to put it in the heap? But I know the size, right? An array. Splendid array. Which array? Of which data type? Scalar. Am I done? Almost. Copy constructor. I have it. I have the default copy constructor because the copy constructor of an object that has an array inside copies all the values of the array by definition. Because this object here lives on the heap, on the stack. It's a monolithic block. If you ask the dimension of this object, will be 8. Because every float is big 2, the constExp doesn't exist, and so you have 2 floats. Each float is big 4, so the size of this object is 8 bytes. Okay? All clear? So I don't need the copy constructor. I don't need the assignment operator, because the default one is perfect. What? I don't need anything. Or maybe I want to have, maybe it can come in handy a dot product. But why do I need to program something if then I don't want to write functions that I don't need, right? I only want to write functions that I do need. So if I need something, I will add something later. Then you know what is an isometry or not? Well, an isometry is a transformation that preserves the distances of the point and the angles. Okay? A classical isometry is like when you have a rotation matrix. Have you ever heard about rotation matrix? Rotation matrix is a pure rotation matrix is like a little bit less than isometry because the rotation matrix allows only to rotate the object with respect to the origin of the reference. If you want also to translate an object, you have to add a vector, which is the translation vector. The isometries in general are qualified by a rotation matrix and a translation vector. Is that clear? What is the inverse of a rotation matrix? A rotation matrix. But what is it? It's transpose. If you want to, yeah, you have a rotation matrix and you want to invert it, you don't have to say inversion. No, just transpose. Okay, and this comes in with the very definition of identity. Because if you take R transpose, right, then this means that you take the matrix and the same, right? Once you do the definition of the inverse is that a matrix multiplied by its inverse is the identity. So far, so good, right? And how do you prove that the inverse of a rotation matrix is transpose? Well, you write this expression, R transpose, and then you write the identity aside. Then if you take the first vector of the first row vector of the matrix, and the first vector, first column vector of the matrix, and the first row vector of the first row vector of the matrix and the first column vector of the transpose that are the same, first and first, and you do the product, basically it's a unit vector that is multiplied by itself, and so the result will be the squared magnitude of the vector, which is 1, and you get the first element of the transpose. All other vectors are orthogonal pairwise, and so basically only the vectors, only the first with the first, the second with the second, and the third with the third give 1. All other products give 0. That's how you prove it. But De Luca will take a longer than me to just blutter it. Okay? Now, isometry has a matrix, right? Oh, let me also write this. I want to be consistent. You might also have isometries of 3 dimensions. And what is the minimal number of parameters that I need to describe a rotation and the translation on the plane? The minimal number of parameters. In 3D. In 3D I need, no, in 3D I need 6. Okay. In 2D, minimal number. 1 rotation, 1 translation on the X, 1 translation on the Y. 3. Because the rotation matrix is fully qualified by 1 in 2D, it's fully qualified by just 1 parameter, 3D. All right. Just created a vector of 3 dimensions. I might need it. Fine? Okay. Then just, I don't love it, but come on. No, it's not 2, it's dim. Better? So I just populated. That's what you do. When I have a matrix, like when I have an isometry, I might want to represent it. And I represent it with a rotation matrix, which has dimension by dimension and translation this. Okay? You like it? Very good. Do we like it? I don't. Better? I just deleted the vector because I have this other function because maybe I need it. And let me populate some function. Oh. I just write all the functions here. This is a trick. I just want to be sure that the variable is a scalar, so I explicitly say that it's a scalar. This will turn float of 0, double of 0, or whatever. Like now, I could have a vector of integers just by changing that thing, just by changing the code in one point. Okay? I can also put it equals to 0. It will function. All right. Do we agree? What else do I need? Maybe in the constructor of the isometry, I might want to initialize the matrix. I want to have a set identity here, because what is a transform that doesn't change anything? The rotation matrix should be the identity, because there's no rotation, and a point gets projected where it is, and the translation vector should be 0. Right? So I will write a method here, just for fun, which I call set identity, right? That will fill the rotation matrix with 0, 1, 1, 0. Okay. Basically, I'm scanning, and rotation of RC is equal to 1, only if phi is equal to C.
In efficiency level, is more efficient to this, or it's the same?
If I trigger on the optimization, this loop will not be done, because the compiler knows how big is the dimension, knows everything. It will unroll the loop, and it will find a pattern that initializes it in one go. Probably it will create a constant, and it will either do a mem copy or do some register operations that zero it.
So it's better than doing
this is static code, and this is compiled brutally. You can also put an if. The compiler will, the compilation process will detect it, and will eliminate all useless branches, because it unrolls the loops. You don't see the for. There's no branching in this code. There will be no branching in the generated code. I mean, if you're speaking assembly, right? All right. And then basta. Do you see what I written? Or if you want me to be verbose, when I have to set it the identity, when is a thing 0, if R equals C, rotation R equals 1. I mean, it's completely equivalent, because when you turn on the optimizations, it will be 4. I think we have written too much code, right? We have to compile now.
the value of this function go into a
Absolutely. The value of this function should go, your colleague says, should the value of this function go in a CPP file? If you want to do the old-style programmer, this is actually what I'm trying to teach you. Now I write everything in the header for didactic purposes. Then I will move it in the CPP, unless you want to use a special keyword. And the special keyword costs an humongous time of compilation time. The special keyword is called inline. If you write inline, you're telling the compiler, dear compiler, don't compile this code. Or compile it, verify it's correct, but then for every time this function will be called, don't generate the call activation style, don't generate everything. Take this code, expand it in line, in the assembly thing, and run the optimizer on it. So like, you will not have the overhead of passing the parameters or anything. Everything will be expanded and optimized on the spot. So if you have a huge matrix or a huge matrix expression and all the things are in line, then the compiler finds itself all the information it needs in the context, which means that it will start substituting the invocation variables into the generated code. Is that clear? So if you write in line, this function doesn't need to appear in the CPP, but we pay a lot in terms of compilation time. In general, if the function is atomic and small, making it in line is actually recommended. But if the function is huge, or it does a lot of things, no, you don't want to put it in. Is that clear? You pay, compilation time is an issue. Ah, and then what else do I need? Come on, did I really set the identity? Are we happy? More or less. No, there is something I made wrong. There is something I made wrong. So let me check. This is fine. This is fine. Oh yes. This I made wrong. There was one more parenthesis. Okay. No. I'm losing a parenthesis. 4. Emacs died. Possible. Okay. And why don't you indent it correctly? Aha, I know. Okay. Fine. Let's compile now. And so of course I will need to do something, but then I can't compile this stuff because there's no code, there's no geometry to the CPP for generating the library, right? So I just comment this line. No, I don't comment it. I changed my mind because what I don't have are the print functions. How am I gonna see that this stuff works, right? I would like to have in the geometry today something that allows me to print a vector. Do you agree? Or to print a matrix. So let me write down some print functions. Help me. For sure I will need to include the IO stream. And these print functions actually, then these print functions, I will put them into the CPP file. Why? Because the print functions are the most slow thing you can ever do. And they will anyway invoke calling and calling and calling. So there's absolutely no advantage in expanding in line something that codes a thing that takes days. Okay? Inline expansion is good only when you have a huge expression to evaluate, you want to copy the code so that some simplifications can be made. But if in this inline function you call something incredibly expensive, it's not worth it. You just pay compilation time and you don't gain anything. Right? All right. So, help me. I would like to write a function that takes a vec3 What am I doing here? Of course, I will move it in the CPP in a while. Here I am, standard.stream, because I didn't include the namespace. I need something to print the stuff. I'm declaring a function, an operator, a function that will be invoked when I take an output stream, so an object for printing, like cout, and I do greater, or smaller, depending on the set, with a vec2 object. Clear? And this function will calculate, will be responsible of the printing in the thing, and at the end it will return the same object. Now you understand what happens when you print the things with a cout. You're writing an expression, and the expression gets evaluated from left to right. You start, you take cout. You take cout, and then you call bracket with the first argument. And this causes a print. And then the returning argument gets passed to the next bracket operator that causes a print. Then you return the object where you just printed, and so on until you consume all the strings. That's the semantics of the. That's why when we print the strings, the things in C++, we will cout greater first argument, greater second argument, and so on. And so on. By doing so, basically you are evaluating an expression when you write. When you write, let's do it this way. OS. What is cout? Cout is an instance of an object of type of stream. So you are taking a variable and printing into it. If you open a file, you will ask, please give me an output stream, only that this output stream will write on a file. And you will do the very same thing on that object. So, let's be elegant. What? No. Let's print the values. No, this way. I'm printing all the elements. Search values. Basta. And the space. Anzi, no, not even the end line. So that it's your responsibility to put the end line. Right? So, do you see? And that's a mistake. Why? Like, there was someone that was complaining it's not a good practice to put standard 2 dots, not one single dot. I mean, I want to abolish the insert key. All right. Now, it would be a very elegant thing if I would move the body of this function in the corresponding CPP file, right? So I have to open a file, call it the geometry 2D CPP. Okay. Go here, take this function and copy it there. And then I can try to compile the library at least. Oh. then given that I don't want to ever write std because it disturbs my inner self, I'll just use a using namespace so that I don't have these extra long things. But in the CPP file, I will leave it. In the header file, I will leave it this way. Oh, in the header file, I will leave it with all the qualifiers so that I'm not making it dirty for those that want to use my system. Okay, they don't have imported namespace that they do not want. Clear? There is one thing that was missing. Return. No, I'm returning the output string. Okay. Let's see now. We have the set 0. Let's make it in line. Come on. And then we do. Don't we want to do the same for the vec3? It's elegant, no? Vec3. You have the same printing operator, just to and I think we're ready to try to compile at least. Buffer CMake list this one. So now I have a geometry 2D. I don't add any executable. I just compile this stuff, okay? And let's go here. No, I have a build directory somewhere. Or is it? This one? Yes. Yeah. It started complaining. Let's see. Oh, I forgot a column. Now I can go back to my safe editor because I can compile from there. At least I know the line number. Where was it? Here. And this compile. And you have to tell it build. No? You liked it? But sorry, how comes that it didn't like it? Eh? Eh? Sì, lo so, I know, but I mean, I would like to find the same error here. That I don't. Make dot build, right? It says everything is. No, another. Geometry 731. Oh, where are you? Oh, CPP row 7. Horrible. No, something I don't understand. I know. Now it works. Because that -c is the flag for telling make to compile. Now it seems that everything went well. How do you know it? You do this, then you make it a little bit larger. Go here, Alt-X compile. No, it works. It didn't do anything bad, but again, okay, it went. Okay, now I have it, but it's really like too early to do anything. So the other thing I would like to do is to start the binary, right? To have a test program for what I written. Let me write some more stuff. What else I need? Because then you will have to complete these things. What else do I need? I need a function that initializes the transform, that calculates the inverse of a transform. Might need it, no? And what would be the signature of an isometry? What it would be the signature? What, like, how would you write the method inverse? Inverse. The method inverse called to an called on an object should return a new instance which represents the contains the value of the instance of the inverse object, right? Correct? Should not return a reference because the reference would require you to allocate memory somewhere for that object, but you can't because it's a reference. It's living on the stack and it will be destroyed once you exit the stack frame. Okay? So, what is the inverse of this thing? I'll tell you immediately. Or, I will introduce another inline, isometry 2. I will introduce another how to say, another qualifier, which is const. If you write const at the end of a method, you are declaring that the object on which you call that method will not be modified. Why do you do it? You can also avoid doing it, but if you do it, you are protected in two ways. Because if you try to modify an object which is declared const, then the compiler warns you. Because you know by design when you have to put const. You say, oh, this shouldn't, I calculate the inverse of this value. The value should not change. I just calculate the inverse. First thing. Second thing, if you try to do it, the compiler will, if you try to modify something in the inverse, if I would try to change some of these elements of the invocation object, the compiler will tell me, no, I don't let you do it. Either you remove the const or you change your way of operating. Clear? Okay. So the inverse is the transposed. Is there a way of transposing a matrix without copying it? Yes. Yeah, swapping. Like I'm doing the transposition in place, as your colleague said, like by swapping the things without having to create a new matrix. Okay? And then what about the translation vector? The translation vector becomes minus R transpose times the old translation vector. Spoiler for De Luca. I have to do this, I don't like it. No.
No. Restriction R,C, come aperta quadra intervalla.
Ah, ho sbagliato. So I made a mistake, sorry.
Ah,
I made a complete mistake. It's like, you can also do this, but you can also redefine the bracket operator. Don't do that. No, it's actually quite elegant because you could have element access on its data type as if it was a vector. In the standard library, it's constantly done. Okay? Fine? You like? Very good. Mm-hmm.
with the auxiliary variable, we can say inverse transfer.
Restart.
With the auxiliary scala, we can say inverse of cost or the difference.
I made a mistake. Yes. I made a mistake. Thank you. I was just inverting in place. That was horrible. Isometry to dest. That's the destination. Okay? Okay. Dest dot set identity. Yes. It was horrible mistake on my side. And then I don't need all these panegyrico here because I was doing the inversion in place. This would be inverse in place. So what do I need to do here? Okay, dest dot rotation RC. Then I don't need to do all this stuff. Okay, I have to create another variable. I made a mistake, a horrible mistake before because I was focused on constructing the inverse, but that's not the game. In order to respect the signature of this function, you have to create an object, and into that object you have to write the inverse. In my brain, I was doing the inverse in place, but I would have spotted it because once compiling with const, it would tell me, hey, you can't do that. Okay? And then this becomes all much easier. Huh? That's consistent. My mistake. Sorry. And then there's the last thing that we do with isometries. There are other two, but the other thing that we do is that we tend to multiply these matrices. Now you compose the transformations. And once you compose the transformations, you have a rotation A, rotation B, translation A, translation B. The result is rotation A times the two rotation matrices get multiplied, and the translation vector becomes the translation vector of the first matrix plus the rotation of the first matrix multiplied by the translation of the second matrix. So to say, yes, if I want to implement, let me write also the expressions. if you allow this notation. Will it work? I don't know. I mean, the exercise that, I mean, I don't know if now 43, so we're getting long. But I will now write down for you to complete for the last time, but we go easy, okay? A set of operations on these objects that at the end ultimately need to support the expression. What we will need is a chain of transform that describes the position of an object onto an object, because we would like our simulator to be able to support object on object. So you can have a robot, on the robot you could have a sensor, on the sensor you could have something else, and so on. And then we would like to have something that moves the things in an harmonic manner. Basically, there will be a main loop that at every point in time it will trigger a kinematic update, which means moving the objects according to the motion law. We will calculate the next state of the object, and then at this point we will do something, maybe rendering the sensor scan, rendering that we have the information in the state, and we will be doing it. Okay? So the functions that I would like you to implement, I mean, did I lose you or still I have you? Are you following somehow? But we want to test this stuff, and for testing it, let me do two functions more. One function which is a constructor for the isometry that takes a vector 3, a vec3, which is which contains the xy and angle, xy theta. So we have to populate an isometry by the rotation matrix is cosinus sinus minus sinus cosinus of the angle. So float a scalar x we extract the field. You can also do this. This will not generate any overhead on the compiler, but it's all, you know, this way you're saying, oh, I want to have an alias. It will not generate any code. Just like pick up the things. I have to populate the rotation matrix. So cosinus sinus. This is the rotation matrix, and then there will be errors for sure. Plenty of, but still. Now we have a method, a thing that initializes the isometry from the vector. And then we would like also to have the opposite. That extract from the isometry a vector that contains the same thing in a way that I can do in and out, and I can have my first testing loop. I can move from xy theta to angles and stuff, and then move back, and I want to figure out whether they are the same. Help me. What do I need to do here? I want to return a variable of type vector, and I want to have that the method toVector that extract xy theta from a rotation matrix will not hurt me. Okay, will operate. So for sure I need to create a variable a copy of a variable that then I will give out, that I will return. So I will need a vec3. Best, call it this way. Okay, and after doing that, what else do I need to do? I need to copy value, pass the things. So in particular, vec dest dot values dot so of 0 will be equal to translation dot values of 0. Right? There will be plenty of errors, don't worry. And then dest values of 1. And then what about theta? There's a function that is called atan2. It's the arctangent, but it takes the x and the y, so that it disambiguates the quadrant, because the atan has the periodicity which is pi, and atan2 resolves that. You have to play, the syntax is atan2 yx. So I can extract the angle from the rotation matrix, but just by calculating the atan2 from sinus and cosinus, and I see that sinus is in the position 1, 0, and cosinus is in the position 0, 0. Okay, makes sense? Now we have the minimal thing for testing this stuff, because what we could do is to take a vector, any vector, like x, y, theta, calculate the transform, and then multiply this, calculate the inverse, and then we can go back to the vector space, and then we should be able to see at least that the angle is the opposite of the angle, because the inverse of a rotation on the plane rotates you back of the same angle of the first, but in the opposite direction. Okay?
Do we have atan2 in ISP? Do we have atan2 in ISP?
iStream is only for streaming. 8 and 2 might be in math, CMath. If it's not, I will include it. I don't know where we have it. I mean, now we will have a plethora of errors. No, no, it's not. Okay, you see, atan2 is not existing, and what do we do? CMath. No. Let's see, now plenty of errors. I'll fix these errors, and then isometry 2 dest. Yes, of course, when I created the constructor isometry 2 without default constructor, the system complains because this constructor over here overrides the default constructor. So I have to provide a default constructor. Annoying. Provided the default constructor. Let's see. What other errors do I have? Int 0 equals r. Here. Oh yeah, this is a genius. R equals 0, no? C equals 0. Okay. Die. Operator quadra, yes. Operation, translation, dest, translation, that's values. And translation doesn't have values. No? Because translation is an object of type vec2. Let's see. Test values of R. Dest translation values of R. Okay, now it compiles. We don't yet know whether it works, but that's one thing, guys, that really disturbs me. Shall we gift to this vector the possibility of accessing the fields with a bracket operator? So that we can do vec instead of going to the field translation? Isn't it a good thing for your heart? Cool, eh? And we have also to add the const counterpart. Because if we don't add the const counterpart, it will you can't invoke a const function from a const function. You can't invoke another function which is not const. And we have two versions of the operator bracket. One that lets you modify the object and returns you a reference to the element in position I, and another version which returns you a const reference to the element in position P. And we do the same. We have the power now of accessing the things element by element. And we are so proud of it that we repeat it also for the other. I mean, you notice that I do it on purpose, of doing this stuff, because once we will introduce the template, we don't have to generate a new class for everything. And so, to vector, let's see if I can blast everything. I mean, first compile. And it compiles. Second, now that I introduce the bracket operator, I can have a much lighter syntax. I hope you... translation, yes. Blast. Destroy. Può essere? Mo lo cerchiamo. Dove sta? Dove? Coseno, seno. Ah, sì. 0, 1, 1, 1. Sì. Copy and paste. First of all errors. Yes. Okay. Did you see what we have done? We have simplified our syntax by simply telling to the C++ that if you have one of these objects, vec2, and you call it an operator, and by passing one integer, then you want to access the thing. I tell you one thing. You can also put a list of arguments here, and you can have a bracket operator that operates on a list of arguments. You can also overload the operators. Will it work? Probably not. Now, I want to really, last year people complained because we were going too fast during the simulator and stuff. This year I want to take the opposite approach. Now I will put on the web when I arrive at the office today some header things and some test elements. Okay, let's say by this evening, because now I have 3 hours of exam after this lesson. And I'd like you to try to do it and to test it. It will be just completing this linear algebra stuff. One thing that I might expect you to do is to implement the multiplication of poses, no? Multiplication of transforms, so that you get ready for the first lesson, true lesson of robotics 1. And that will be one thing. And then based on this, we will build the rest of our architecture. Okay? Doable, easy, busy. At 12, this lesson finishes, so I think it's finished.
When we introduce the bucket bracket operator,
Yes.
we did two
Okay. That's a good question. Before you leave, we decided to implement two versions of bracket operator, one for the const and one for the non-const, right? And one says, why the hell do I need to do that? Perfectly legitimate question. Now, the compiler is a program, right? It's not an inventor. It doesn't conversate with ChatGPT. No, nothing like that. No, it works on your machine based on the knowledge it has. And now, how do I, as a compiler, how do I ensure that a function is const? I have to check that this function calls only other functions which are declared const. If one of the functions in the chain is non-const, so then the containing function can't be const. Now, this operator here returns a reference to a scalar that would allow me to modify the values. And if I call this function, I potentially could change the invoking object. While in this case, I return you a reference to a const scalar, which means I return you a reference to a position, but it's constant. You try to modify it, says, no, it's constant. Clear? Now I will push this stuff, and then we will continue.